Good morning, everyone. Welcome back. At the time of this recording, the exam is still going on, so I do not know uh, any information about the second exam yet. But we are starting a new chapter, and our new chapter is Chapter 6 Reactivity and Mechanisms. This is where we really dive deep into the organic chemistry, and we're going to go real fast, so it's time for everybody to buckle down. Buckle up, here we go. So we're about to go on a very long ride that's actually going to be ending pretty soon because it's actually the midpoint in the semester, and I can't believe that the semester has already gone by that fast. I call it a semester, but really it's just the 1 month summer session, and we're already 2 weeks through. So who would have thought you could get through organic chemistry this quickly, right? All right, so let's get started. This is chapter 6 on chemical reactivity. Let me switch the view real quick. There we go. Chemical reactivity and mechanisms, and we're going to start out by discussing enthalpy. Oh, my arch nemesis, enthalpy, and I say that because of the that chart we had back in lecture 5 or something, or maybe it was lecture 6. That was an enthalpy delta H chart where it was showing the release of energy from a combustion reaction with negative delta H's, and I somehow thought that was a heat of fusion, not a heat of combustion graph. So again, my nemesis, just because of that one incident, right? But now we're gonna dive real deep into this enthalpy stuff. Not so much the math, so I don't want you to really figure. This next chapter will probably be the most math that we ever do, but again, I'm not going to be focusing much on the math. I'm going to be focusing more on the actual chemistry part, so don't worry so much about the math. All right. So enthalpy, or delta H, or Q, as it were, is heat energy exchanged between the reaction and its surroundings. Right. So when you break a bond, you have to have energy to do that, and the energy is absorbed into the system, and so electrons have to absorb enough kinetic energy so that can overcome the stability of that bond. Okay, and so what you see here um, is the molecular orbitals. What you see here is molecular orbitals, right? And it looks like a hydrogen gas molecule right there, 1s, two 1s orbitals, and then a sigma bonding orbital right here, right? And it's low energy. And so you have to absorb, the electrons have to absorb enough kinetic energy to overcome the stability of that bond right there, right? Of that bonding molecular orbital. So bonds can break either homolytically or heterolytically, and this is what I was alluding to previously in earlier slides, where you could actually have a homolytic cleavage bond cleavage, right, where you get radicals as a result. Okay, and basically what a radical is a species that has one electron and another species that has the other electron, right? Previously we were talking about how only electrons that were in um, pairs could move, right? Like in resonance or in the acid-base stuff, But they can do a homolytic cleavage, right? Where one electron right here goes to the Y, and the one electron over here goes to the X. And then you end up with two radicals, okay? And you know that a radical cleavage or homolytic bond cleavage is about to happen when you see arrows that look like this, right? They have this one-sided arrowhead, right? Or like this, right? One-sided arrowhead. That's the dead giveaway that you've got a radical reaction going on. In fact, I spent not my entire graduate time in PhD school learning about radical reactions, but a lot of it because we were studying uh, this molecule called SAMe. And I don't know if you've ever been to GNC or those health stores that they sell all these like supplements that don't really need because they're just going to pee them out, those those places. Oh, you know what I'm talking about. The place where I told you to go and ask the guy if they knew, the guy or the girl, whoever was working there, if they knew what omega-3 fatty acids actually meant, because it's actually omega-3 and not just omega-3. Remember that? No, I don't think that was your class. I think I said that to somewhere else. I think I said that in a different class. Anyway, so the point is, I was studying this molecule called SAMe. More specifically, it was SAM, S-adenosylmethionine, right? And S-adenosylmethionine is a cofactor that's used in building huge molecules using radical chemistry, like with maybe the synthesis of cobalamin, right? Which is vitamin B12, which you know your body needs. And so it uses radical chemistry, and you see things like carbons moving from one spot to another spot. It's kind of crazy like that, right? But there's definitely radical chemistry. It's real radical, right? So, but you can purchase SAM, right, from SAMe or SAM, S-adenosylmethionine, at GNC, which is actually kind of a waste of money, because if your body didn't have SAMe, I don't know if you would be alive. So I guess you could increase your SAMe concentration in your body, but the thing about it is that your body can only absorb so much, and you end up peeing the rest. And most people get their SAMe from what they eat in their food, right? So unless you are vitamin deficient, right, or anything like that, and your doctor says you need it, then yeah, don't buy SAMe. It's expensive. Like one bottle costs like $30, $40. I mean, oh my God, you're making it naturally in your body right now. Anyway, so that's radical cleavage right there, right, or homolytic cleavage. There's also heterolytic cleavage, is what we're most familiar with, right? For example, when we have like an acid, right, and then a base comes over, and it pulls off the proton, and that happens like that. Right, so what's essentially happening here is that there's a bond forming, right, between the base and the proton, and then the bond between here, the proton, and the acid, right, or the conjugate base in this case, breaks, okay, and you see that these arrows here have a double head, right, which means there's a pair of electrons going, right, and so what this part right here would be, right, would be the heterolytic cleavage, right, where the electrons from X go completely over to Y, and that's why you end up with ions, right, X plus here and Y minus over here, because Y minus has the entire pair of electrons, which gives it an extra electron, so that's why it's minus charge. X lost an electron, right, and so it's positive charge. So in this case over here with my acid-base example, my Lewis acid-base example, because there indeed is a transfer of electrons. There's always a transfer of electrons, right? You form BH, right? And you get also a minus, right? If B just happens to be a nitrogen, right? Like an amine, like so, right? And that B equals nitrogen, right? Then now this BH has 4 H's, and it would make it a positive charge, just like the X plus, right? But sometimes you have bases that don't have, that are. Sometimes you have bases that already have their full octets, or they're slightly deficient 1 electron, right? So it could have just been the sodium amide, right? Where you had the negatively charged amine, like this, and it already had a negative charge on it too, right? And that could have worked too that way as well. But the point is, at the end, you have ions at the end of a heterolytic cleavage, and that's mostly what acid-base chemistry is. That's what Lewis acid-base chemistry is, right? It's a transfer of a pair of electrons. So all this comes down to what we call the BDE, or the bond dissociation energy. Basically, that's the delta H required for the bond breaking of a homolytic cleavage, right? And the next couple of slides are just going to be some charts, I think, of some bond dissociation energies. And as always, excuse me, I've got my chair stuck. As always, I don't ever like want you to memorize things that are on charts like this. Just a general understanding of what this chart is about is all you really need to know. And so, quite honestly, you could take these bond dissociation energies and figure out, how much energy is required to break a bond, right? So, like, you have a carbon hydrogen bond here in a methyl, and it requires 435 kilojoules per mole, right? Does that make sense? You have some hydrogens, like these acids right here, right? Hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, right? I mean, you can see a trend here where the fluoride, which is the most electronegative, right, requires the most, right? Whereas the iodide, which is the least electronegative, requires the least amount of bond dissociation energy, right? Just in these trends right here. Okay. And you can see then that the range here is from about 300 to 600. Okay. And there's, it's fluorine to iodide, right? So that's a trend that you can see there. The more electronegative something it is, the more, when it's connected to the hydrogen in like a potentially acidic species, the more bond dissociation energy is required to break that bond. Okay. The proton off of a water takes about 500. That's a lot, right? That's pretty high up there too. I think the next slide is more. Yeah, so there are more. You can see here we have carbon-carbon bonds, right? Carbon-carbon bonds, as you can see here, from here to here, right? They're all in the 300 range. All right, carbon-carbon bonds are all in the 300 range, so that's something you need to kind of commit to memory. Not the exact numbers, but just know if you're trying to break a carbon-carbon bond, it's going to be about 300, right? And you'll see that this actually corresponds to the energy that's in UV rays, right? UV rays are like around 300 to 400 nanometers, right? Something like that. And if you were to put that into an equation that would convert nanometers, which is also energy, into kilojoules per mole, you would see that 400 or so nanometers right there is just about 300 something, kilojoules per mole. I don't want to go through the math because I don't want you to have to focus on that, but I just want you to know that that if you convert the nanometers of UV light into, which is in nanometers, right? Convert it to kilojoules per mole, it's actually around 300, right? And so 300, 350 around there is the same kind of energy that's required to break a carbon-carbon bond, right? So if you've ever wondered why going into the sun gives you skin cancer, literally the reason why is because there's tons of UV light coming from the sun, and the sun, right, for giving you all that UV light is hitting your cells, and guess what? In your cells is made up of mostly carbon-carbon bonds. DNA, right? Your DNA is mostly sugars, right? Deoxyribose nucleic acid, right? So the ribose part is all sugars, and so, which is all carbon, right? 6 carbons, 5 carbons, but in this case, deoxyribose, and or ribose is the sugar itself, and so you get hit by UV rays from the sun. It passes through your skin cells, goes into the nucleus, hits the backbone of your DNA, right? The the ribose sugars of your deoxyribose nucleic acid, right? And it just happens to be the perfect amount of energy to break those carbon-carbon bonds that are in your DNA, and that's why you end up with getting skin cancer, right? So it's kind of interesting stuff. Um, so carbon bromine, like carbon to halide, right? Ones, right, or even to alcohols, right? You can see that there's a difference here, right? Because carbon to alcohol is like almost 400, which is kind of high, but a carbon to an alkyl halide, right, is in the 300s. I mean, sorry, the 200s, right? So those are the kind of trends that you need to be aware of. Okay. So bond dissociation energies, right, directly relate to the exothermic or endothermic nature of a reaction, right? So most reactions that involve most reactions involve multiple bond breaking and forming, right? And so in an exothermic reaction, the energy gained by bonds formed exceeds the energy needed to for the bond to be broken. So the in other words, more products are more stable than the reactants, right? And that's an exothermic reaction. That's the part that you need to remember there. In an endothermic reaction, though, energy needed to break bonds exceeds the stability gained by the bonds that are formed, right? And that's an endothermic reaction. But just to, the part that you do need to remember there is that the products are less stable than the reactants in an endothermic reaction, right? Those are the two things you need to remember. And honestly, we're just going through like definitions right now, so it's best that you just try to memorize the parts that I tell you that are important. So let's take a deep dive here into what it means to be exothermic and endothermic. So here we have an exothermic reaction. Here's your enthalpy, or delta H, right? Your delta H, and on the y-axis, and then reaction coordinate is basically the progress of the reaction. And on a exothermic reaction, you have your starting materials, right, at this particular delta H, and so or enthalpy. And as the reaction progresses, it goes up over this hump here, and this hump here we'll learn a lot more about later, but it's called the EA, or the activation energy. And after it gets over that hump of the activation energy, it starts to form the products. And the thing to notice here is that the delta H, right, of the products right here is much lower than the delta H of the reactants, right, or the starting material. And that's why it's negative, right? That's why it's negative. And so an exothermic reaction always results in a negative delta H, right? Products are lower in energy. Energy is released as heat. That's basically potential energy, right? That's in these molecules right here, right, during the reaction. And it's converted to kinetic energy in the form of heat. And as already said, delta H is always negative, right? And the sum total of all of this is that the temperature of the surroundings increase, right? The temperatures of the surrounding increase because the reaction is releasing heat, right? So a really good example of that, right, would be I don't know if you were all here in February when when we had the deep freeze and we had no power and we had no water. Maybe some of you were lucky enough to not to have to deal with that, but my house, we literally lost all the power, all the water, all the gas, right? And it was like in the negatives in our house, and we we're tough tough Texans, so we didn't want to go anywhere, right? So we huddled up and tried to stay warm. And one of the things that we used was those little heat packs that we use, those hand warmers that we use at football games when it gets too cold. And literally, what happens is, I actually have one, you know, because you got to keep them safe, just in case you need them for another, you know, deep freeze. So yes, I have this in my emergency, you know, closet where I keep all my emergency rations and water and all that stuff. And these are like hand warmers. And quite literally, what's happening here is when you open up one of these hand warmers, the reaction of the material inside, the starter material inside of this packet here, will react with the water and the air, right, and become very hot, right? Very, very hot. It's releasing a lot of heat. Okay, and so that's how these hand warmers work, because they actually are an exothermic reaction. Another good example would be if you ever were in the military. I was in ROTC for a very long period of time, and we had these MREs, and I guess you could buy MREs at survival stores these days, but they had these little packets in them where you could put your dang, I wish I had one to show you. I probably do somewhere, a really old one, but it's probably all moldy now. But you could open this like packet, like it was like a plastic bag, and it just looked like a translucent plastic bag. And you opened it, right, and you added water to it, and then you put your food in it. Say it was like, you know, Stromboli for that day, right? No, actually, I think we had like Frankfurters or something like that. That was a very common one. But anyway, you put those in there, and still in the package, of course, inside the plastic bag that had the water in it, and the water had this little plate in it, right? And it would react with the water, and it would get it really hot, and that's how you heated up your food, right? And so that's another example of exothermic reactions. So on the other hand, we have endothermic reactions, right? And the thing to notice here is that the starting material is already low in energy on an endothermic reaction. Okay, it still has to go up and over the activation energy, right? But the end products right here are higher in energy, right, than the starting materials energy, right, enthalpy. And that's why in an endothermic reaction, the delta H is positive, right? And also, this time, kinetic energy is converted into potential energy, because energy is actually being absorbed by the system, right? By the reaction, okay? Energy is consumed. So, of course, delta H is positive, and this actually results in a temperature decrease of the surroundings, right? So it feels like it's getting cold, right? So a good example of that would be like those ice packs, which I have also in my first aid kit, where you break them, right? You just like shake them up and you break them, and then they get cold, right? And they get cold, and you can use, you know, these instant ice packs, and that's an example of an endothermic reaction. I feel like I'm always sort of trying to prepare for some survival, event or something like that. Who would have thought what happened in February would happen in February? But that was a tough time. That plus the pandemic, holy crap. Anyway, so I'm spending a lot of time on this because just knowing the basics of an endothermic and an exothermic reaction, and the basics of an I just said that. The basics of an exothermic and an endothermic reaction is super important, right? You need to know these basic things. I'm not going to make you know the math, but you need to know these things at least. Okay? Like the calculations, don't even worry about that. I'm going to go over them briefly here, but you don't even have to worry about that really. So, just a quick little summary of it all. The plus sign and minus sign of a delta H indicates the reaction as being either exothermic or endothermic. An energy diagram is often used to describe the kinetics of thermodynamics of a chemical reaction, right? So potential energy then is described by the y-axis, the same axis that you would use to have the delta H on. Reaction progress is described by the x-axis, right? Or in the previous slide, it was called the reaction coordinate. So that's the step you are in the progression you are on the actual reaction itself. So those kinds of things are super helpful, you know. Practice on Skill Builder 6.1, predicting the delta H of the reaction on Wiley Plus. And what it means by that is just predicting whether or not it's going to be exothermic or endothermic based on its charge, right? Not charge. I mean, that's not an electron or a proton. What do we call it? Sign. It's sign, right? Positive or negative. Okay, so let's just keep on going with this a little bit further here. And I alluded to this earlier when we were looking at the chart, right? You can use the bond dissociation energies, right, to actually determine whether I think a fly was just in here. It's so weird. Where do these flies come from? My dogs are letting them in probably through the doggy door. Oh, I forgot. Somebody, one of your classmates asked if they could see my dog. So, well, I have 3 of them. I have what looks like a Chiweenie, and then I also have, and he's kind of small. His name is Kovu, and then I have another one, a Corgi. Her name is Kiara, and then I have a big German Shepherd. His name is Yogi. So I'll show you one of them right now. Kovu, come here, kid. Come here, buddy. Okay, we're gonna go full screen so you can see him here. Here you go, buddy. Come on. I know. It's not even raining, and I'm making you get up. This is Kovu. Hey, look, buddy. Look at the screen. Look at you. Look at you right there, buddy. Come on, buddy. Look. Okay. You're a little camera shy, huh? It's okay. Here, let's turn this way. Maybe you can see it now. Look at it yourself. Look at you, buddy, on the camera. Do you see it? Yeah. You doing good, buddy? You doing good? You doing good, buddy? He was sleeping, so. But at least he listens to me. Okay, buddy. Back to lecture. Thank you for coming by. Okay. Back to lecture. Lost my train of thought. Oh yeah, so I alluded to this before, where you can use the bond dissociation energies to determine whether or not a reaction is exothermic or endothermic, right? And so here you see a propane. I don't know why I put so much emphasis on that. And you see a bromine, right? And you know, bromines, they're one of the diatomics, right? Where they have to be like, you know, they can't just be a bromine atom by itself. It has to have 2 bromines together. And so we have bromine gas and a propane, right? And we're forming this guy here. Okay, we're forming this guy here. So how do we form this guy here? Well, the first thing that has to happen, right, is that we have to break a carbon-hydrogen bond right here, right? We have to break that bond and break bond. There was a fly in here. I almost killed it. Missed it. I used to have another dog, and his name was Zuko, named after Prince Zuko from Avatar: The Last Airbender, and we had to put him down recently, which is super sad. But he used to chase flies and other insects in the house, and I really wish he were still here, so he could take care of this fly for me. And not just that, I miss him, but he was damn good at chasing insects. Yogi, on the other hand, not so good. Not any of the other ones. So you have to break this bond right here, this hydrogen-carbon bond, right? And then you also have to break a bond here between the 2 bromines, right? Got to break that bond too. God, flies. It's the same fly. I just can't get that dang thing. Anyway. And so, got to break that bond there too, between the two bromines. Oh wait, that's break like car brakes. Whatever, you get the point. And then you have to form a bond between a carbon and a bromine. And you have to form a bond here between a hydrogen and a bromine. All right. Right, and you can actually look up all these different bond formings and bond breaking energies on that chart, right, in your book. Okay, and so the bonds broken here equals the dissociation energy, bond dissociation energy there for carbon hydrogen, which is 397 kilojoules per mole, and then bromine, which is 193 kilojoules per mole, right? The bonds formed will be between carbon bromine and hydrogen bromine, right? Hydrogen and bromine. So delta H equals the 397 plus the 193 from here and here, from bonds broken, minus the 285 and the 368 from bonds formed here and here, right? And that gives you negative 63 kilojoules per mole. And that makes it so that it is an exothermic reaction. That will happen. That will happen readily, right? No interference needed. Okay. So there's not just enthalpy that you have to worry about. There's also entropy, right? Entropy is delta S, and quite simply, delta S or entropy is disorder, right? How disordered things are, and so. Right here, see, molecular disorder. That's all you really need to know about that, right? And just so that it's, you have a formal definition, entropy is the number of vibrational, rotational, and translational states the energy of a compound is distributed, right? Well, you'll see the implications of that in a second, but just remember that delta S entropy is molecular disorder. So let's look at this visually, right? Consider why a gas will expand and spread out into an empty container, right? So we have here a stopcock between two glass Florence flasks, right? If you didn't know, a round bottom flask is actually known as a Florence flask, which is actually, I'm pretty sure that's right. If I'm wrong, tell me down in the comments below if you're watching this on YouTube. And so what can happen here is this stopcock, you can turn it, right? And you can open it up so that the stopcock is in line with the pipe that's in there, right? And then when you do that, the gas molecules will flow from this side right here to this side over here to expand and fill in take the shape of its container, just like we learned back in CHEM about gases and the states of matter, right? So the number of states the molecule spread across increases with increasing volume, which makes sense, right? Because the more volume a gas has to spread out, the more ways it can move around. And that's what it means by the number of states, right? The number of states. So when I was talking about that previously over here, I went next. There we go. Over here, with the number of vibrational, translational, and rotational states. I mean, that literally is the more ways, right? A gas molecule can move around, whether it's rotating, vibrating, or moving side to side, up and down, right? The more volume there is, right? The greater the entropy, right? Because the more of those ways that a molecule can move around. So the total entropy, or delta S total, will determine whether a reaction is spontaneous, right? Which means it will happen no matter what, right? So delta S total equals the delta S system plus the delta S surroundings, right? So the entropy of the system plus the entropy of the surroundings will give you the delta S total, and then disorder, basically a measure of disorder. And Sorry, I just got a notification on my iPad. So the delta S total will equal the or the entropy total, or the total number of this amount of disorder, right, is equal to the system's total amount of disorder or entropy, right, plus the uh, uh, surroundings amount of entropy, right, or disorder. So for chemical reactions, we consider the entropy change for both the system, which is the reaction, and the surroundings, which is usually the solvent, right? So yeah, remember that the triangle always means delta, which means the change in something, okay? So if delta S total is positive, then the reaction is definitely spontaneous. Oh, Kiara just woke up, if you heard that. Whew, so let's keep on going. I know there was a lot of math, and there will be more math, but don't worry about it too much. All right, let's just keep going. So the delta S system, right, is affected most significantly by two factors, right, and will be positive, okay? Where there are more moles of product than are reactants, right? So right now the reactant is a single molecule, right? And then in a decomposition reaction, it breaks down into two molecules, right? Two molecules, okay? And that's that's any decomposition reaction that you can think of, where just there's nothing actually reacting with it; it just decomposes, right? And so in this case, you had 1 mole of the reactant, and you end up with 2 moles of products, okay? That will cause a delta S system to be positive. And then another way, right, is if you have a cyclic compound, right, and it becomes acyclic, right? It becomes acyclic. And in both of these, right, you're heading towards more disorder, right? Because you started with 1 and now you have 2, okay? Or here you had the cyclic organized into a nice little circle, and now you've broken it open, right? So both of these are going towards more disorder, and these will affect the delta S system, right, to make it positive. Oh, sorry, checkpoint. Conceptual checkpoint 6.3. Go check it out on Widely Plus. Check it out on Widely Plus. So recall that the spontaneity of a process depends only on delta S total, right? Again, this is the reaction. The equation we have. Delta S system plus delta S surroundings gives you the delta S total, right? So it turns out, though, that delta S surrounding is a function of the delta H system, or the enthalpy of the system, right? Or the reaction. And its temperature, okay? And its temperature. So the delta S surrounding then can then be organized in such a way that now delta S surroundings equals the negative of delta H system, right? The enthalpy of the reaction divided by the temperature, okay? Which gives us this new equation for delta S total, which is delta S total equals the negative delta H system divided by T plus delta S system, right? So again, a lot of math there, but it's okay. Just hang in there with me. Temperature is important in this kind of thing, right? Because adding temperature to something will make the system more disordered, right? Like when you're boiling water, right? You're making water molecules that were liquid, right? Nice and organized liquid. And then you're heating it up, and now they become a gas, and they vapor just flying around everywhere, more disordered, okay? They used to be all in this pot of water, but now they're in the air, right? So temperature plays a big part in all of this. It's probably why this is called thermodynamics. So, yeah. You dive real deep into the mathematics of thermodynamics when you get to physical chemistry. We won't be doing that here. So, that brings us to talking about delta G. You're like, oh my gosh, how many deltas are there? So delta G is Gibbs free energy, right? And to get delta G, you multiply both sides by temperature, right? So you multiply this equation right here, right? You multiply both sides of that by temperature. That means you multiply this by temperature, you multiply this by temperature, right? And you multiply this by temperature. Okay? Multiply that by temperature. Okay? So when you do that, right? When you do that, this here becomes this guy right here, right? What does it become? It becomes T delta S. T delta S, right? TAS. Okay? And then if you multiply temperature by our new S surroundings, right? Delta S surroundings, right? What do you get here? Well, that's simple. This cancels out that. Those two T's cancel out that. And so what you get here is going to be, negative delta H system by itself, right? And then over here you get T delta S total, right? So in the end, your equation will be T delta S total equals, right, negative delta H system. That's not how you say system. System, right? And then plus T delta S, right? So that's the equation you get, and that's the equation you see on the next slide, which is this one right here. Okay? Okay? I know it says, it doesn't say minus there, right? But all that happened there is that we switched the signs over so that now this is the positive and the other two are the minuses, right? Still consistent with this here, right? Because still consistent with this here because here we have positive delta S total, positive delta S, right? System, delta S system, right? And then negative delta H system, okay? Which is still consistent with having negative delta S total, positive delta S system, delta H system, and negative negative T delta system, delta S system, right? So these equations are equal to each other. This one right here is the same as the equation that I wrote here. Okay? So now that we have this equation, the reason why we had to do that, make everything opposite signs, is because negative T delta S total is actually equal to our new thermodynamic parameter, which is delta G. Right? Delta G. Okay? So there used to be this joke, right? Because back in the day, when I was back in organic, not an organic lab, but I was in the research lab back at Sam Houston State University, and I was notorious for somehow setting off the fire alarm. Like almost every week, the fire alarm would go off in the chemistry building at Sam Houston State University, and it was inevitably my fault. Like one time I made the autoclave explode, one time this is going to be the example for delta G right here. One time I left the water running on one of our instruments and forgot to turn it off, and the water hose, I had it in the sink, the waste hose in the sink, right? But somehow it popped off with the instrument, and so when it popped off the instrument, water started flowing out into the freaking, not into the sink, but like onto the floor. And it was like that like the entire weekend. And yeah, that was bad because we got there the next, like on one day, and there was like leaks from the third floor because that's where my lab was, coming down to the first floor, and we were like, what the heck's going on here? So we go up there, and my entire lab is soaked. It's like underwater, okay? And so we used to make this joke, right, that oh, don't worry about it, Gibbs Free Energy will take care of it, right? Which is what that basically means is that if you just leave it alone, eventually it will dry up, right? Okay, so you'll see how that connects to what I'm about to say here, right? So Gibbs Free Energy, or delta G, right, is um, so sorry, let me say that again. A negative delta G value delta G means that it's spontaneous, and a positive delta G value means it's non-spontaneous, right? And so the action of water evaporating on its own without any kind of like, that's a spontaneous reaction. Okay, so that's a negative delta G right here, right? So the point is though that delta G takes into account all the thermodynamic parameters that we were just speaking of, which is delta H, right, enthalpy, delta S, which is entropy, and temperature, right? Because also the temperature of the room will assist in the evaporation of all that water that flooded my lab, right? So just like it says down here, the delta H is associated with the entropy, right, and the entropy of the surroundings, right? Because remember, this used to be the delta S surroundings, right? And because this used to be delta S surroundings, and we found that delta S surroundings is equal to the negative delta H divided by temperature, right? Remember that? So that's where that comes from. So not only does this delta H here take into account the enthalpy because it's delta H, but it also takes into account the change in entropy in the surroundings because it was before delta S surroundings, right? Before we did our equational equivalencies, right? And then over here we have T delta S, and that's associated with the change in entropy of the system itself, right? Good stuff, good stuff. So do you see how we went from, what happened here is I tried to stepwise go through with you how we went from this equation up here, right, which is delta S total equals delta S system plus delta S surroundings, and got it to the point where now we have delta G, delta H, and delta S all in one equation. Okay? Knowing how to do that is not as important as knowing that. Okay? Remember. The other thing to remember too, if delta G is negative, it's spontaneous. It will happen no matter what happens. You don't have to interfere with it, right? Whereas if delta G is positive, it's non-spontaneous. It's not just going to happen. Okay? So let's look at some examples of some delta G's, right? So, or some free Gibbs energy, not free Gibbs, energy for, no, am I dyslexic? No, I don't think so. Gibbs free energy, there it is. I just get mixed up sometimes, the words get mixed up. So Gibbs free energy examples here, right? So for example down here, consider the following reaction, which is spontaneous, okay? We have here a diene and an alkene, and it will cyclize into this cycloalkene, right? Cycloalkene. Since this reaction is spontaneous, the delta G must be negative. Okay, must be negative. We also know that T delta S will be negative because entropy is decreasing, right? 2 molecules became 1 molecule here, right? Remember in the previous slide I said how you went from 1 molecule to 2 molecules, right? That was disorder. You're increasing disorder, okay? But now 2 molecules just became 1 molecule, right? So that's actually becoming more ordered, and you're decreasing entropy, okay? So it must be true that all delta H, so it must be true that delta H is a negative value for delta G to be a negative value overall, okay? In other words, the entropy of the surroundings is increasing more than the entropy of the system is increasing, right? So that means that it was releasing heat or some kind of energy, right, into its surroundings, right? Which is another reason why This is also an exothermic reaction. Okay, exothermic reaction. Again, just remember the basic stuff. Okay. So that takes us to the kind of the vocabulary words that we use with Gibbs free energy. Okay. Notice on this chart that now instead of having on their delta H, right, or enthalpy, we have Gibbs free energy, and the reactants, of course, up here, the starting materials, you still have to go through up to the activation energy. You have to overcome the activation energy, and you'll get your products. And this is very similar to a exothermic delta H plot, reaction plot, right? But instead here, instead of calling it an exothermic reaction like you would in delta H or in enthalpy terms, when we're talking about delta G or Gibbs free energy, when the delta G is negative, it's exergonic, right? It's exergonic, right? Exergonic, and that's a delta G, okay? And this in particular doesn't necessarily mean a release of heat, but it means that, unlike it is over an enthalpy chart, right? It means that this reaction will be spontaneous. Like it's likely to happen, right? It's likely to happen. So, if a process has a positive delta G, then it is not spontaneous, right? So the opposite of our last slide, and that process is endergonic, right? Which it favors the reactants. And you'll find that a lot of the reactions in our biochemistry, like in glycolysis, are actually endergonic, and they require enzymes, right, to catalyze those reactions to push them through, or they would never happen on their own, right? And notice that we have a positive delta G here, and so it's endergonic, and so it's non-spontaneous. Okay? So, back to equilibrium then. Okay? Consider that an exergonic process with a negative delta G, right? Why is it, though, that if it's a spontaneous reaction, why is it, though, that it never ever goes to completion? Like, you have 100% products, right? Well, the reason why is because an equilibrium is reached. And what that means is that as more and more reactants, right, start becoming products, there will be less reactants around to bump into each other, like collide with each other, so that there would be more reaction happening, right? Because remember, all this is based on collision theory, right? A molecule of reactant has to collide with another molecule of reactant in such a way, in the right orientation, with just the right energy, right, for it to actually react. But as the concentration of those reactants decreases, that kind of stuff, that perfect storm for a reaction to occur, becomes less and less frequent, okay? And so, you'll get to a point where the rate of making the forward reaction, which is making products, will be the same as going backwards and making the reactants again, right? And that point is called the equilibrium point, right? And obviously, though, if it's a spontaneous reaction, the equilibrium point will be such that the products will be the most in supply, right? It will be the highest concentration. It will be the most of the say that a reaction is 0 to 100%, right? In a spontaneous reaction, the products will be the vast majority of that 100%, right? Just for Shigego's say 80%, right? And you'll have 20% products, and that line there between the 80 and 20 is the equilibrium point, right? Is the equilibrium point, right? So, in this case right here, in this particular slide, your products are A and B, and you're making C and D, right? It's definitely exergonic, spontaneous with a negative delta G, right? But you're never going to get 100% C and D because it will eventually become equilibrized. Equilibrized. It will actually it will eventually come to equilibrium, right? And like I said, the rates of making the products will be the same as the rate of making the reactants, and so that's where we stop getting more products and stop getting more products, and that's because on the reactant side, there's just not as much collision happening anymore, right? So this is something you need to know, just before I move forward. The greater magnitude of the delta G negative means the greater concentration of the products in the equilibrium, right? Okay. Oh, I just did it again. Everything I just told you in the last slide is happening right now on this slide. Okay, where why doesn't an exergonic process, right, a spontaneous process like with a negative delta G, go to 100% of products, right? Well, it's because once as the reaction progresses right here, right, the concentration, right, of A and B decreases, right? So collisions will occur less often, right? Eventually, the forward and reverse reaction rates will be equal, and that's your equilibrium point. Okay? That's your equilibrium point. I'm not going to rehash this because I just said it in the previous slide. But luckily for you, I didn't write out everything I said, so here's the slide that talks about that, and you can just study this slide. It basically summarizes everything I just said. So we can always, like we were talking about before with acid-base equilibrium, we can always put this into an equilibrium equation, KEQ equation, right? Where KEQ equals the products divided by the reactants, and the products are always the concentration of the products, right? So in this case, if C and D were the products, you can multiply them by each other, and then divide that by the concentration of the reactants, A and B, and then you'll get the KEQ, right? So what's interesting about this, though, is that you can determine, this stuff. You can determine this, these variables experimentally, because delta G equals the negative of the of R. What is R? Is that the ideal gas constant? I think that's the ideal gas constant. Tell me below, tell me in the comments below if you're watching this on YouTube if I'm right, but I'm pretty sure ideal gas constant is R. And then the temperature of the system, natural log of the KEQ, right? So you can literally experimentally determine those things, plug all that stuff in, and you can get a delta G for it, right? Good stuff. Practice with checkpoint 6.6 on Wiley Plus. KQ, delta G, delta H, and delta S are all thermodynamic terms. They only describe the relative stability of the product and reactants, but they do not, but not the rate at which the products are formed, right? The products or the reactants are formed. We haven't even gotten a rate yet. Yes, and we'll see that in just a second. Okay, so now we have a chart that shows some equilibriums, some KEQs, right? Some chemical equilibriums, and their corresponding delta Gs. Okay, notice up here when we have a delta G of negative 17, the KEQ is 10 to the third, which is a pretty big number, right? Not as big as any of those acid-base numbers, but it's pretty big still, right? And at that point, you actually have 99.9% all products and only 0.1% reactants, right? Skip down to the middle here, right, where we have 0 as the delta G, right? And the KAQ is 1. And we have 50-50 of both reactants and products. And skip all the way down here where you have a positive 17 as a delta G. It's what was I saying? Its delta, its KQ is negative. It's 10 to the negative 3, right, which is a super small number. Okay, and now the amount of products you have as compared to reactants is 0.1%, right? The rest of it, 99.99% or 99.9%, is all reactant still. Know this. Know this trend. Know this pattern. Okay. So that brings us to kinetics, which has absolutely nothing to do with the delta G. Okay, the delta G tells you whether or not a reaction will occur spontaneously, right, or not spontaneously, based on its sign, negative if it's spontaneous, right? But the kinetics of the reaction, right, actually tells you more about the rate, right? There are some spontaneous reactions that are super fast, like explosions, right? But there are also some spontaneous reactions that are super slow, like the process of changing a diamond into graphite, right? It turns out that all diamonds, even the one on your engagement ring, right? That one right there, it's at this point, right now, as we speak, slowly turning into graphite, right? It'll take millions of years, but it's definitely going that direction, right? So the point here is that just to know that just because a spontaneous reaction is there, just because you have a spontaneous reaction, it doesn't mean that it's a fast reaction. Okay? So there are 5 factors that will affect a rate of reaction, right? Or the kinetics of a reaction, how fast the reaction occurs. And the first one, of course, is the concentration of reactants. And that makes a lot of sense because if the more reactants you have, the more inside of a little tiny, test tube, for example, the more of it you have, the more collisions are occurring, right? And the more collisions that occur means the faster the reaction occurs. Okay. Next, the activation energy, which is also self-explanatory. Because if you had a activation energy that was super high, all right, as compared to an activation energy that was super low, which one do you think is going to happen faster? Of course, the one that's super low, right? The temperature, of course, and I've already alluded to this before, heating up reactions will make them go faster, right? Because you're actually you're increasing the disorder, you're increasing the collisions that are occurring between the reactant molecules. Geometry and sterics also play a role, right? Because if there are certain groups that are sterically hindered, right, or the geometry makes it so that the perfect part of one reactant can't combine with the other part of the reactant perfectly in the right orientation because of geometry and steric hindrance, that can also affect the rate of the reaction. And last but not least, the presence of a catalyst, which I've already alluded to this before, where a catalyst, right, will speed up a reaction as well, like an enzyme, right, and things like that. Okay. Acids can be used as catalysts. Bases can be used as catalysts. All kinds of stuff can be used. Metals can be used as catalysts too. All kinds of stuff can be used as catalysts. The thing to remember about catalysts is that they're never used up. Okay. You'll go through and you'll turn the reactants to the products, right? But a catalyst will always stay the same at the end of the reaction. So the rate law is determined by this equation here. Rate equals K times the concentration of reactants, right? Which is K is the rate constant. The rate depends on the rate constant and the concentration of the reactants, right? The degree to which a change in the reactant will affect, the degree to which a change in the reactant will affect the rate is known. The rate is known. Wow, that's a really weird sentence. Am I saying that wrong? The degree to which a change in reactant concentration will affect the rate known as the order. Right, okay. We'll elaborate that in a second. Yeah, here, this is where we elaborate it. So the order of the reaction is represented by the exponents of x and y here and here. Okay? So when you have just a rate equals the rate constant times the concentration of one of the reactants, right? the rate of A, right, the rate of reaction is doubled. Okay, and this is a first order reaction. Okay, this is a first order reaction. Okay, and just so you know, this doesn't mean that the only reactant is A. There could be a B as well, right? But the presence of B, its concentration right there, right, doesn't affect the rate at all. Okay, it's just the concentration of A that increases, that affects the rate, and that's called a first order. And the rate is doubled, and it's called a first order because there's only one exponent there, right? A 1 as an exponent there. Here we have a second order reaction. Second order because A is there, 1 with an exponent 1. B is also there with an exponent 1. This time B, right, does affect the reaction. Okay, the concentration B does affect the reaction. Still second order. If A is doubled, then the rate is doubled, right? And then we have now a third order, right, where A has an exponent of 2, B has an exponent of 1. What that means then is, quite simply, since the 2 is here, it's squared, right? And so if A is doubled, the rate is quadrupled, right? But since B only has still 1 there, right? If B is doubled, then B is still just doubled, right? And we call this a third order reaction because the addition of those exponents, 2 and 3, make it a third order reaction. Okay? 1 plus 2 equals 3. Okay? I think the thing that people have to remember about this slide is that it's showing the doubling of the rate, right? Doubling of A makes double the rate, or doubling of B makes double of the rate, right? So just its presence means, of either A or B, means that it's going to double the rate if you double that reactant, A or B, right? Like it is here in the second order and the first order rates. Okay? So its absence of B here just means that B don't do anything to the rate at all. Okay? But then in the third order reaction here, right, since A has a 2 up, a square by it, right, when it doubles, when you double the concentration of A, the rate is quadrupled, right? What's not stated here, though, is that if you double the rate of B, does that quadruple too? No, because its exponent is still only 1. Okay? Good stuff. So now let's go into activation energy. I told you we'd elaborate on this more. So the activation energy is the barrier between the reactants and the products, right? The energy barrier, okay? The activation energy is the amount of energy required, the minimum amount of energy required for molecular collision to result in a reaction, okay? So again, we have our potential energy chart like we always see here with the reaction coordinate over here, which means the progress of the reaction. Not delta A, EA, or activation energy is literally this gap right here between the reactants and this peak. That's the activation energy, right? And there has to be enough collisions and enough like heat or whatever, right, to make it so that you have enough energy for the reactants to beat this hump, get over this hump for it to go down to being the products. Okay? And that's what activation energy is. So it makes sense that if you lower this down a little bit, right, make the peak a little lower, it would increase the rate of the reaction. Okay? Activation energy, again, it increases. As it increases, the number of molecules possessing enough energy to react decreases, which makes sense too, right? Because if you have a higher activation energy, right, you're going to be needing more and more energy to get to that hump, right? And eventually you're going to run out of energy, and so the energy needed to react decreases. Oh, sorry, I said that wrong. Not the energy needed to react decreases, but the reactants possessing enough energy to react decreases. Okay? So lowering the activation energy means faster the rate, which I said that already before, right? And I literally drew this out for you in a previous slide, right? Here we have a relatively low activation energy. Here we have a relatively high activation energy. So what that means then is that we have a faster rate here, a slower rate there, right? Their drawings are prettier than mine, so maybe you should just go with theirs. All right, another thing that can affect the rate, which I said before, I'll write too. Temperature. Raising the temperature will result in a faster reaction. Okay. At higher temperatures, molecules will have more kinetic energy, which makes sense because you're throwing heat in there. It's getting hotter in there, man. They're just bumping around, right? And what is kinetic energy? The energy involved in the movement, right? So higher temperature, more molecules will have enough energy to produce a reaction, right? And in this chart here, it shows at lower temperature, right, the number of molecules with less energy. And then over here, we have the number of molecules with higher energy, right? So you definitely have higher energy. You have molecules at higher energy with higher temperature over here, right? Because that's what you're shooting over here. More delta E, right? To get more molecules with higher energy to get to the delta E. No, sorry. The EA, the activation energy. Sorry. The activation energy. I don't even know what delta E is. Change in energy? I'm confusing more. Forget that. Forget what I said about delta E. It's EA. Then, the third thing that affects the rate is steric considerations, of course. Steric hindrance and the geometry of compound can also affect the rate of reaction. When molecules collide, they must have the correct orientation for the bonds to be made or broken, which I said that already before. If the reactive conformation of a compound is higher energy, it will spend less time in that conformation. So the probability of collision is resulting in a reaction is low, right? Big thing to remember there, right? Steric considerations, steric hindrance, they have to be in the right conformations, right, for them to be able to collide in such a way so that they can have in the correct orientation for bonds and to be made or broken. You can explore that. We'll explore that further in Chapter 7. It's the next chapter, I think. And last but not least, certainly not the least, because it's the thing I deal with the most as a biochemist, right? Because enzymes are catalysts, okay? Catalysts speed up the rate of reaction without being consumed. Enzymes are, oh my god, I didn't even know that said that. Hey, shout out to the biochemist. Enzymes are catalysts. Catalysts provide an alternate and faster pathway for reaction. Catalysts lower the activation energy, right? So quite literally, if you had here's another reaction coordinate diagram, okay? And you had a reactant, right, with this certain amount of potential energy, and its activation energy was super high, like this, and this is like the vast majority of your metabolism reactions, your metabolic. This is the majority of the reactions that happen in metabolism, right? Where they have a high activation energy, right? And an enzyme is required to bring down that activation energy so that your metabolism functions properly. And what an enzyme does, or a catalyst does, is that it brings down the activation energy by bringing the reactants into these intermediate and fleeting structures, right, that are lower energy, just so that you can get to the lowest energy of the products, right? Okay. So there are more steps in an enzymatic reaction as far as going from the reactants to the transition states and the intermediate steps of the reaction and then down to the products, right? But it still happens much faster because the activation energy is much lower, right? For each of those smaller, transition states / intermediate structures, right, that are between going from A plus B to C plus D. Okay. Recall that kinetics and thermodynamics are completely different concepts, right? I just said that. I mean, I flogged that dead horse a million times, okay? Kinetics is involved with the rate of the reaction, whereas thermodynamics is about the equilibrium of the reaction, right? So notice that we're worried about in thermodynamics the delta G, but here in kinetics we're worried about the activation energy, right? Oops, went too far. So now we have to talk about the difference between the thermodynamic product of a reaction and the kinetic product of a reaction. Okay. Consider the diagram in which describes two possible reaction pathways for A plus B, right? A plus B could either go up here like this to become E and F, or it can go down here to become C or D, right? The formation of the product C plus D has a lower activation energy, right, the blue line, and are lower energy in, and its products are lower than energy C plus D, lower than energy than E plus F, right? So what that means then is that the C plus D forms faster, right, because it's got lower activation energy, and, excuse me, C and D are also more stable than E and F because its final potential energy is lower than E and F's. So what that means then is that C and D here, right, are both kinetically and thermodynamically favored, right? So C and D here would be both the thermodynamic product and the kinetic product, right? Okay. Take those. So when you're looking at a reaction, right, the point is you have to be able to see the reaction and like one of these charts, and take into consideration the kinetic factors and the thermodynamic factors, right? And decide whether or not a certain product versus another product is either the kinetic product or the thermodynamic product, or one of them is both the thermodynamic and the kinetic product, right? And in this case, C plus D is the thermodynamic and the kinetic product because kinetically it's got a lower activation energy, and then thermodynamically it's got a lower potential energy, the final product does, right? So here is a reaction that's not going to have both of them, not going to have a product that's not going to be both kinetically and thermodynamically favored, right? So here, now in terms of the formation of E and F versus C and D, right, according to this diagram, the formation of the products E and F has a lower activation energy, right here, okay? Thus, E and F will form faster, okay? Then the C and D are lower in energy, thus are more stable than E and F, right? So the formation of E and F is the kinetically favored, but the formation of CD is the thermodynamically favored, right? So C and D in this case is the thermodynamic product, right? And then E and F, right, they're the kinetic product. Kinetic product, okay? Be able to know that, be able to tell the difference by using the chart, okay? And just to reiterate, E and F is why? Why is it the kinetic product? Because it has a lower activation energy, right, than C and D does. Now let's talk about transition states and intermediate states, right? You didn't just think that a reaction happens and then you get like A plus B and then boom it becomes C plus D, right? No, it's got to change and go into different states and then become that, right? So let's first look at this reaction coordinate diagram and know the parts first, right? Everything in green here is known as a transition state, okay? And then everything in orange is known as intermediate, right? Notice that transition states are higher energy than intermediates are, right? So what do you think is more fleeting, right? Just from that. Well, obviously it's going to be the one with higher energy because molecules don't want to stay higher energy, right? So transition state's going to be more fleeting, right? Where intermediates are going to hang around a little longer, right? That has a lot of implications, and we'll see those in the coming slides, I think, right? Whoever made this PowerPoint, I hope they, it's borne out in what I said just now. Could have been me that made this PowerPoint. Who knows? The transition state versus the intermediates. What is not observable, right? So, just like I was saying, transition states, they have high energy as the reaction passes through, right? They have super high energy. So they are fleeting and they cannot be observed, right? High energy cannot be observed. They're not around long enough for you to be able to actually see them, right? And so a transition state here between bromomethane and chlorine, or chloride rather, to make bromochloride and bromine, right? Or bromide, right? What's happening at this transition state is literally this. The bond between bromine and carbon is breaking, right? That's what those dotted lines are. And then the bond between chlorine and carbon is forming, right? So this is a transition state, right? It's actually literally happening right now in this picture. The forming of a bond and the breaking of a bond, okay? And that's a transition state. And generally it happens quite quickly. It's very high energy, and that's why you can't observe it, okay? Whereas in an intermediate, okay? You can observe it because it's got lower energy. Lower energy, right? There's not a bond forming, right? Here we just have a positive carbocation on a isopropane. Yes. Okay. An intermediate is an intermediate species formed during the course of reaction, and they are at the energy minima, right? Intermediates are definitely observable. They are actual chemical species that exist for a short period of time before they react further, right, to become that. That's the difference between the two. That brings us to the Hammond postulate, okay? The Hammond postulate states this, right? 2 points on an energy diagram that are close in energy should be similar in structure, right? So based on this assumption, we can generalize that the structure of the transition state is dependent on whether or not the reaction is exothermic or endothermic. Okay? So in this reaction here, it's definitely exothermic. Okay? Because the resulting products have lower energy than the starting material, right? And you can see here, right, this is a transition state, okay? And the bond breaking and forming here, right, is occurring such that you can see that the bromine is getting further and further away from the carbon, whereas the chloride, is getting closer and closer, right? Getting closer and closer to the carbon, okay? What does that mean then? What that means then is this, right? In an exothermic reaction, the transition state resembles the reactants. But in an endothermic reaction, the transition states resemble the products. Why? Because the reactants are closer in energy to the transition state in a exothermic process, whereas in an endothermic process or an endothermic reaction, the transition state, right, is closer in energy to the products. Okay? Whew. Practice, checkpoint 6.7, right? Oh, sorry, that's a 6.7 right there where my head is, right? Wiley Plus, just for you. That actually ends today's assignment, right? Or ends today's lecture. And lucky for you, since this is not the end of talking about reactions and reactivity and mechanisms. There will be no quiz or assignment assigned today in lecture, right? But for sure there will be one tomorrow. Just a reminder, you do have an exam 3 on Friday on June 18th, 2021. And my apologies, that is a typo right there. It shouldn't be by the end of the day today. It's actually by the end of the day tomorrow. Right? Because your lab midterm is on Tuesday, not on Monday, and I think today is Monday. So so it will be due by the end of the day tomorrow. It will be posted by 8 o'clock tomorrow. So my bad there. All right. Hope you enjoyed this lecture. I'll have information on the last test for you probably in tomorrow's lecture, or maybe even the exam solutions video. Okay. Have a good day. Take a little break, right? Because there's no assignment or quiz. See you tomorrow.